Alrighty, howdy folks. Let's look at chapter 11 section 2, which is about series. In section 1 we looked at sequences. Now we are graduating to what are called series. What's the series? Definition: a series sigma a sub n is the sum of the terms of the sequence a sub n. That is, sigma a sub n, which automatically means is the index n is going from 1 to infinity. When you don't write the index at all, it's understood to be n equals 1 to infinity. But it doesn't have to be n equals 1 to infinity. For instance, you could have n equals 5 to infinity. That's perfectly possible, okay? But usually it would be 1 to infinity, sometimes even 0 to infinity. But anyways, what exactly is this? This is nothing but a1 plus a2 plus a3 plus all the way up to a sub n and further on. Does that look familiar? What are these stupid a sub 1, a sub 2? Oh, they are nothing but the terms, the first term, the second term, the third term of a sequence a sub n. Right? In a sequence, what we did is we took the terms a1, a2, a3, a4 and just comma separated them. Whereas in a series, we are actually adding them, adding all those terms. That's the whole difference. Now, please pay attention to this. If I asked you, hey, what is a sub n? A sub n is the nth term. Good. Nth term of what? Of both a sequence and a series. Right? A sub n could be the nth term of a sequence, or it could be the nth term of a series. Keep that in mind. Right? Now, you might think, that is stupid, man. You got infinite terms and you are adding up all of them? What's the deal with that? There's no way that when you add up infinite number of terms, the sum could be anything but infinity. Right? Maybe here is what you're thinking intuitively. And there's nothing wrong with that. Let me put it this way. If I said, hey, what is 1 plus 1 plus 1 plus ... infinity, infinite number of terms, and you'll say, oh, obviously infinity, right? Okay, what about a much smaller number? Let me put it this way: 10 to the negative 1000 plus 10 to the negative 1000 plus 10 to the negative 1000, so on. 10 to the negative 1000 is just ridiculously small. Did you know that? We are talking about 0.99901. So that is a very, very small number. Okay, what if we make up a series containing terms that small? Unfortunately, even this adds up to infinity. Right? So now you're like, oh, wait a minute. So there is absolutely no point in adding infinite number of terms. Check this out. Let's say I have a pizza. Super Bowl time.
Pizza is a dish of Italian origin consisting of a flat, round base of
Alexa,
dough
stop.
with a topping of...
So if I have a pizza, and let's say it's Super Bowl time, and I ordered me a nice large pizza, and before the game started, the fat guy that I am, I chowed down half of it. Cool. And at the halftime, I ate half of what was remaining, which turns out to be 1/4. Right? And after the game, I ate half of remaining one, so 1/8. And in the night, because of way too much beer drinking, I got a bit hungry and hit the refrigerator, heated the 1/16 in a microwave and ate that. Right? So I keep doing this. Notice what I'm doing. Each time I eat half of what is left over. So first I ate 1/2, then I ate 1/4, 1/8, 1/16, and so on. Now, by the time I'm done, how much pizza would I have eaten if this process continues, each time eating half of what is left over? There's no way that this could exceed 1. It has to be equal to 1. Right? Wait a minute. So I do have an infinite series here that when I added up all the terms, the sum turned out to be a nice finite number. So at least there is one instance where that is true. So that gives us the confidence that, this thing about, adding the terms of an infinite series is not just a futile exercise. There is some value to it, and some series do converge, meaning their sums add up to a finite number, right? And that's why we are interested in infinite series. And in fact, this is, are you familiar with something called Zeno's paradox? Zeno's paradox is, would Achilles beat the tortoise? And the tortoise is, say, a certain distance. Their destination is a certain distance. And tortoise has been given a head start of, say, 100 meters. And the argument, Zeno's argument says, well, at a certain amount of time, the distance between Achilles and the tortoise would be, in the beginning, it is 100 meters. After some time, their distance would be one half that. And at a later time, 1/2 of that. So, according to this calculation, you will see that there is no way that you can keep on doing this half, and there's no way that Achilles would even catch up with the tortoise. What's the deal here? The thing is, at that time, they did not know about infinite series, and they did not know how to add infinite series. And there's the concept of, once the concept of limit was brought up by Leibniz and Newton, all those kinds of, that Zeno's paradox just evaporated. All you need to do is take the limit of something. As long as you're taking limits, all those problems just disappear. Okay? All right. With that, now I need to define something called a partial sum. The partial sum S sub n of a series is sigma A sub n is given by S sub n is A sub 1 plus A sub 2 plus A sub 3 plus ... plus A sub n. What? That just looks like that original sigma A sub n, man. No, there is a slight difference between the original series and the partial sum S sub n. And the difference is, notice, we stop with the nth term. We start adding terms. We start with the first term, add the second term, third term, and so on. But when we get to the adding the nth term, we stop right there. So S sub n, the nth partial sum, is just the sum of the first n terms of the series. That makes sense? You add the first n terms of the series to get the nth partial sum. Based on that, could I ask you what S sub 1 is? Think about it. Can I ask you what S sub 1 is? Oh, okay. You start adding. Start with A sub 1 and stop adding when you get to A sub n. When I say S sub 1, what is my n? 1. Okay. So you start with adding A sub 1 and keep going until you get to A sub 1. Oh, wait. So that means S sub 1 is just A sub 1. Yep, you're right. Oh, okay. Let's see. What is S sub 2? Well, start adding A sub 1 plus the... Have you reached A sub 2? Because n is 2 here. Have you reached A sub 2? Nope. I have A sub 1. Okay. Plus A sub 2. Have you reached A sub 2? Yes, I have. Okay. Then that means you stop right there. You get the idea? That's a good way of thinking. It comes in very handy in many other situations too. Okay. What is S sub 3? You start by adding A sub 1, and when you will stop when you get to A sub 3. So that means A sub 1 plus A sub 2 plus A sub 3. Cool? All right. Now, can I ask what is S sub infinity? Notice I put it in quotes because there is no such thing as S sub infinity. While technically I am not supposed to say S sub infinity, you get the idea, right? S sub 1 and S sub 3 is A sub 1 plus A sub 2 plus A sub 3. So what is S sub infinity? Well, A sub 1 plus A sub 2 plus A sub 3 plus ... all the way up to A sub infinity. But wait a minute. Isn't that the same thing as the whole series? Is this S sub infinity related to the sum of the series S equals sigma A sub n, which is A sub 1 plus A sub 2 plus A sub 3 plus ... Yeah, S sub infinity is nothing but the whole series, right? S sub infinity is equal to S, which is the sum of the infinite series. So the question is, how do we find this S sub infinity? How do we find the sum of the series S, right? And my answer is, you will find it from S sub n. Take a look at that. How do we find S sub infinity? You will from S sub n. How, man? S sub n is just a sum of finite number of terms, A sub 1 through A sub n. But we are looking for a sum of all the infinite number of terms, whereas S sub n is only a sum of finite number of terms. Right? That's the idea. So what we'll do is, we will come up with an expression for S sub n. Right? We'll come up with an expression for S sub n, and then take the limit of that S sub n as n approaches infinity. That's our strategy. S sub n, when you take the limit of it as n approaches infinity, you are sort of finding S sub infinity, or S. Okay? So here is the idea. That is, to find the sum of a series, we find an expression for S sub n and take its limit as n approaches infinity. Cool? I know it's a bit of theoretical explanation. I hope you're okay with it. Cool? Now, with that, I need to talk about a geometric series. We looked at a geometric sequence, so this shouldn't be all that hard. A geometric series is of the form sigma AR to the n minus 1. The first term is A. The second term is A times R. The third term is take this AR and multiply by R, you get AR square. And to get the next term, multiply this AR square by another R, you get AR cube, and so on. And also it turns out that the nth term is AR to the n minus 1, and you continue like that. So that is a geometric series. So the question is, just now I discussed how to find the sum of a series. And I said what? you find an expression for S sub n and take its limit as n approaches infinity. And immediately I jump to a geometric series. Is there a connection between my stating, hey, to find the sum of a series, find S sub n and then take its limit as n approaches infinity, and immediately talking about a geometric series? Yeah, because I can now ask you, tell me, is there a way to find sum of this geometric series? And immediately you should say, yeah, there is. What we'll do is we'll find the S sub n, the nth partial sum of this series, and take its limit as n approaches infinity. So what is the first order of business? Our first order of business is to find S sub n, that is a plus ar square plus dot 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 ar to the n minus 1. Right? That is those are the first n terms, and we are adding them up, and that is S sub n. Yeah, but do we know a formula for this? Yeah, there is a formula that you learn in pre-calculus or algebra 2 or someplace like that. Which is okay. So a plus r, this is a times r to the n minus 1 over r minus 1. Okay, somebody broke something. Uh-oh. Sorry about that. So a times r to the n minus 1 over r minus 1. So that's the formula for S sub n. So our strategy is we'll take the limit of this as n approaches infinity, and tada, we get the sum of the geometric series, this infinite geometric series. But before I do that, let me start with 3 plus 6 plus 12 plus 24 plus 48 and all of this. Right? Let's see. Is this a geometric series? A good way to finding whether a series is geometric or not is to take, say, the second term and divide it by the first term. So 6 over 3 is how much? 2. So now, once you get the common, what could be potentially the common ratio r to be what it is, now take the second term, multiply by that common ratio that you found, 2, and see whether or not you get the next term. Did I explain it right? Let me repeat that. Second term over the first term, 6 over 3 is 2. Now, take the 2 and multiply the second term, 6. Do you get 12? Yep, we do. Multiply 12 by again that same 2, you get the next term, 24. 24 times 2 is 48. So that tells you that this must be a geometric series. Right? Now, what is n? How many terms do we have? 1, 2, 3, 4, 5. N is 5 in this case. So let's see. And what is a? A is the first term, and a is 3 here. And what is the common ratio r? 2. So we know a to be 3, r to be 2, and n to be 5. So let's plug into this formula. Cool. A is 3, r is 2, n is 5. So if you plug into this formula, sum should be 3 times 2 to the 5 minus 1 over 2 minus 1. 2 to the 5 is 32. 32 minus 1 is 31. 3 times 31 is 96. 96 divided by 1. 3 times 31 is 93. 3 times 32 is 96. 31 is 93, and that's equal to 93. So let's see. 3 plus 6 is 9. 9 plus 12 is 21. 21 plus 24 is 45. 45 plus 48 is 53. 93. Right? So that is not, so this formula did work. Isn't that cool? Right? So with that, let's go to the next one. King and chess. Can I tell you a story? Okay, it just so happens that the story goes, there was a very, very rich king in India, and he was an avid chess player. And he was pretty good at it. He used to beat everybody that he played. And he kind of got bored of this winning, and he said, hey, go ahead and announce there's a promulgation. Whoever beats him in chess will get whatever they want. And so there is a poor Brahmin. Brahmin is it's a caste in Indian thing. So anyway, a poor Brahmin, this guy, he tries his luck. And it so happened that a whole bunch of them tried with the king in anticipation of beating him, but they could not. And finally, this Brahmin goes and plays and surely beats the king. And the king says, man, go ahead. What do you want? And the Brahmin says, I want some rice, king. You want what? Rice. Rice. Are you kidding me? I'm the king here, and I'm giving you an opportunity to ask for whatever you want, and you ask for rice? Ask for diamonds, gold, silver, man, come on. And the Brahmin humbly replies, no, king, thank you very much, but I just want some rice. Okay. Rice it is then. Okay, how much rice do you want? And the Brahmin says, how much? And, well, not a whole lot. See, I just want enough rice so that I could put 1 grain of rice in the first square of the chessboard and 2 grains of rice in the second square of the chessboard, and double that 4 in the next one. That's all. I just want to be able to do that for all the 64 squares. And the king just laughs at this guy's stupidity. And of course, this is all being done in the king's court, and a whole bunch of people are watching this whole spectacle, and they all laugh. What a stupid guy this guy is, man. I thought, because he beat the king in chess, he must be really smart. Turns out he's an idiot. Really? Was this guy really such an idiot? The thing is, we now know exactly how much he asked. For example, did he ask 2 to the 0 grains in the first one? And in the second one, 2 to the 1, 2 square, 2 cube, 2 to the 4, and so on. And so by the time we get to the 64th square, isn't it 2 to the 63 grains in the 64th square? And not only that, he gets all of them. Right? We need to sum up all of that. Wait, why am I talking about this stupid story in this context? You guessed it, right? This is nothing but a geometric series, the sum of a geometric series. So, what is n? What is a? A is the first term, 1. What is the common ratio? 2. How many terms do we have? N is 64. So if you plug it into this, a times r to the n minus 1 over r minus 1, we get this, right? And how much is that? That turns out to be 1.85 times 10 to the 19 grains of rice. That is the amount of rice this guy asked. Isn't that cool? Let's do a bit more calculation. Apparently, a grain of rice is around 29 milligrams. What's a milligram, man? I know. I'll eventually convert it to pounds for you to be able to relate to it. So 29 milligrams. but that is nothing but 1.85 times 29 is 53.65, this many milligrams. So milligrams, to convert it into kilograms, you need to divide by 10 to the 6. And so this many kilograms. Okay. And now 1 kilogram is 2.2 pounds. There we go. So I multiplied 53.65 by 2.2, and so you get this. So that is that's it. Wait a minute. So this is what? This is 1,000, 1 million, 1 billion, 1 trillion, 1 quintillion, 1,180 trillion pounds of rice, or 1 quintillion pounds of rice is what this guy asked. Yeah, who is the stupid one now? Right? Okay. Cool. That's my story. Where are we? Yep. Our original intention was to find the sum of an infinite geometric series, and we found the S sub n, the nth partial sum. And now the question is, what is the limit of this S sub n as n approaches infinity? That depends, right? Notice a is a constant. The first term is just some number, constant. R is also a constant. So a over r minus 1, the whole thing is just a constant. So when we take the limit of this, all we're talking about is taking a over r minus 1 times the limit of r to the n minus 1. What is limit of r to the n as n approaches infinity? In the sequences section, we learned that it depends on what r itself is. When absolute value of r is less than 1, let me repeat that. When absolute value of r is less than 1, that is, r lies between -1 and 1, limit of r to the n is just 0. Every other case, it's something else. So let's not worry about any other case. We'll just worry about the case where r happens to be between -1 and +1, not including -1 and +1. In that case, that just the r to the n goes to 0, and so we have a over 1 minus r, a times -1 over r minus 1, which is a over 1 minus r, provided absolute value of r is less than 1. So we can actually find the sum of an infinite geometric series, okay, and provided absolute value of r is less than 1. Okay, now determine whether the geometric series, give me half a second, please. Okay, so let's look at a problem. Come on. Determine whether the geometric series is convergent. If it's convergent, find its sum. Okay, let's look at this guy. Is that a geometric series to begin with? Let's see. What did I say? Second term over the first term is 3/4. Figure that out first. Now multiply the second term by that ratio. 3 times 3/4 is 9/4. Yep, that we got the next one. Multiply 9/4 by again that 3/4. Do you get 27 over 16? Yep, you do. So that gives you the confidence that this is in fact a geometric series. Now our question is, does this series converge or diverge? What did we say the common ratio r is? 3/4. Is r absolute value of r? Is that less than 1? What is absolute value of r? is 3/4. Is that less than 1? Yes, it is. So we can confidently say that this series converges. And what is the sum of, what's the formula for the sum of a converging geometric series, infinite series? A over 1 minus R, right? So just plug and chug. A is 4, R is 3/4, 4 over 1 minus 3/4 is 4 over 1/4, or 4 times 4 over 1, that's 16. So really, when you add up all these infinite terms of this series, you get a measly 16. Infinite number of terms. Isn't that fascinating? Cool, let's move on. What about this guy? Hey, there's something else interesting. N equals 0 to infinity. Right? So is this a geometric series to begin with? Let's ask. How do we find that? To me, one good way is to just write down a few terms. What is the first term of this series? How do we find the first term of this series? Any ideas? Hint. N equals 0 to infinity. So, in order to get the first term, we need to plug n equals 0. In order to get the second term, we need to plug n equals 1. For the third term, plug n equals 2, and so on. So let's do that. And when you do that, you get 3 to the 0 plus 1 is 3 to the 1 is 3. Negative 2 to the 0 is just 1. Negative 2, the quantity raised to 0, is 1. And so the first term is 3. The second term is minus 3 square over 2, and so on. Is this a geometric series? Again, let's do what I suggested. Second term over the first term. What do you think it would be? Negative 3 square over 2 over 3. Negative 3 halves. Cool. If you multiply the second term by negative 3 halves, would you get positive 3 cube over 2 square? Yes. If you multiplied the third by negative 3 halves, would you get minus 3 to the 4 over 2 cube? Right? Yep, you do. So this is a geometric series. Cool. What is A? First term, 3. What is R? Negative 3 halves. What is absolute value of R? Absolute value of negative 3 halves, which is what? 3 halves. Is 3 halves greater than 1 or less than 1? Greater than 1. Right? So that's how we proceed. And therefore, what can we say? Series diverges. We cannot find the sum of this, or if you find it, it turns out to be infinity. Right? So that is the idea. Let me pick another one. Same idea. Does this converge, or what's the sum of this geometric series? So, as before, did this. What's a this is a geometric series, trust me. And absolute there's something else I wanted to show you, I guess. Yeah, but we can conclude this is a diverging series because absolute value of R is greater than 1. But when you're given a problem like this, there's another way of determining whether this is a geometric series or not. Can you somehow rewrite this so that it looks like A times R to the n minus 1, sigma n equals 1 to infinity, A times R to the n minus 1? Can we rewrite like that? Okay, check this out. Can I say this? 6 times the top is 2 to the 2n minus 1. Can I write that as 2 to the 2n times 2 to the negative 1? Right? A to the m plus n is A to the m times A to the n. Yep, we can write like that. Cool. Now, 2 to the 2n, can I write that as 2 square the quantity raised to n. A to the mn is a to the m, the quantity raised to n, right? So if I do that, and also notice what did I do? I said 2 to the negative 1 is same as 1 over 2, right? So that's what, excuse me. So I wrote that as 1/2. 6 over 2 times 3 to the n, 2 to the 2n. But then, in the next step, I wrote that 2 to the 2n as 2 square, the quantity raised to n. And 2 square is nothing but 4. So this becomes, by the way, 6 over 2 is 3. I reduce that. And so 2 square, the quantity raised to n. And so this is nothing but 4 to the n. But 3 over 3 to the n is 3 to the n minus 1 over. In the denominator, I can say 3 to the n divided by 3, right? And make this into 3 to the n minus 1. One last step. Notice our objective is to write this in the form of a times r to the n minus 1. So if I have 4 to the n, pay attention to this please. If I have 4 to the n, can I write that as 4 to the n minus 1 times 4? Or 4 times 4 to the n minus 1? Yeah, I can. And so if I do, I have this 4 on the outside, but we have a 4 to the n minus 1 over 3 to the n minus 1. Can I combine that and write this as 4/3 to the n minus 1? Right? Look at the train of how we kept manipulating it. And eventually, did we succeed in writing this as some a times r to the n minus 1? Right? That's the idea. So based on that, we can conclude this must be a geometric series which diverges because absolute value of r happens to be greater than 1. Cool? Yeah. Let me continue. If you want to take a pause, perhaps this is a good place to pause the video. But I'll continue and look at what is called a harmonic series. A harmonic series is very, very, very important series. What do you mean by, I keep hearing, I keep hearing this, oh, it's very, very, very important. What the heck makes it important, man? I'm sure you are asking that. Here, at least in this context, let me tell you. What happens is, in pretty near future, we are going to talk about whether a sequence converges or not, right? Just the previous problem. Did we look at a series? Did I say sequence? I'm sorry. In the previous problem, did we look at a series and did we ask, hey, does this series converge or not? Like that, we are going to look at a whole bunch of infinite series, and the question would be a simple one. Hey, look at this one and tell me, does it converge or diverge? And there, as you try to answer that question, this harmonic series serves as a wonderful counterexample to some claim that people tend to make. In the sense, you will say, because of this condition, ta-da, that series converges. And I will go, wait a minute, that is wrong logic. Harmonic series satisfies that condition, but does the harmonic series converge? So not just in this course, but in future, many places, wherever you bump into infinite series, you will bump into this harmonic series. You will use this concept. That's why it is a very, very important series. And it's a fascinating one. Check this out. What is the harmonic series? Just simple. Sigma n equals 1 to infinity 1 over n. That's it? Yep, that's it. Can you give me the expanded version of this? N equals 1, so 1 over 1 is 1, and plus n equals 2, 1 over 2 plus 1/3 plus 1/4 plus 1/5. That's it. That's a harmonic series. Cool? Question now is, does a harmonic series converge? Right? What did I say about how to figure out whether an infinite series converges or not? There was a strategy that I suggested. And the strategy is, find an expression for the nth partial sum S sub n and take the limit of S sub n as n approaches infinity. Right? Find an expression for the nth partial sum S sub n. Take limit of S sub n as n approaches infinity. Cool. And that's what we did in finding the sum of a geometric series. So let's see if we can apply that same concept to this. The thing is, unfortunately, there is no formula for S sub n. That is, there is no formula for 1 plus 1/2 plus 1/3 plus ... plus 1 over n. There is no formula. If you can find one, man, you can publish a paper. Especially if it looks simple, even better. But there is none that I know of, at least. So here is how we will try to answer that question. S sub 1 is just 1, right? Cool. S sub 2 is 1 plus 1/2, the sum of the first two terms of the series. And now I'll jump to S sub 4, which is nothing but the sum of the first four terms of the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4. Okay. Now let me ask you this. Do you see a difference between these four terms and these four terms? Any difference at all? Yep. Instead of 1/3, I have a 1/4. Now, what do you think? This sum compared to this sum, which one is bigger? Would you agree that the left side sum with a 1/3 should be bigger than this one with a 1/4? Yeah. Why is that? Because when you look at two fractions, say 1/3 and 1/4, which one is bigger? The one with a smaller denominator. The numerators are the same, so the one with the smaller denominator is going to be bigger as a fraction. Right? Why? Well, you have a pie and you divide that into only two people. Each one gets a big piece, 1/2. Whereas you divide that into 20 people, among 20 people, then each one gets 1/20th. Just a small piece. So that's why this left-hand side sum would be bigger than the right-hand side sum. But what is this equal to? 1/4 plus 1/4 is 1/2. 1 plus 1/2 plus 1/2. So I'll write that as 1 plus 2/2. There's a reason why I'm writing it like that. I could have said 2. Instead, I'm leaving it as 1 plus 2/2. What is equal to 1 plus 2/2? This very last thing. So what is the connection between S sub 4 and the last one? Can you say, oh, you mean S sub 4 is equal to 1 plus 2/2? Oh, no. You cannot say that. Be careful. Because this is equal to this, and this happens to be greater than this, and this in turn is equal to this, the relationship between S sub 4 and this is S sub 4 is actually greater than 1 plus 2/2. Okay? I know it's probably the first time you're seeing something like this, but get used to this, please. Okay. And then I'll jump to S sub 8. S sub 8 is the sum of the first 8 terms, which are this. And I'll replace 1/3 with a 1/4 like I did in previous case, and also 1/5, 1/6, and 1/7 with a 1/8, each of them with a 1/8, and then say, this must be bigger than that. Why did I do that? Because I can find the sum of this much more readily. 1/8 plus 1/8 plus 1/8, that is 1/2. This is 1/2, and this is the 1/2. So 1 plus 3/2 is what this turns out to be. And what do we conclude about S sub 8 and 1 plus 3/2? S sub 8 must be bigger than 1 plus 3/2. Cool? All right. Now I can do the same thing and conclude that S sub 16 is greater than 1 plus 4/2. All right. Now, S sub 32 turns out to be greater than 1 plus 5/2. And now my question is, looking at the pattern of all the boxed things, especially start with this S sub 4. Can you say anything? S sub 4 is apparently greater than 1 plus 2/2. S sub 8 is greater than 1 plus 3/2. 16, 4/2. 32, 5/2. Any pattern at all? 4, let me put it this way. 4 is associated with 2, 8 with 3, 16 with 4, 32 with 5. Can you relate those numbers? Guess what? 2 square is 4. 2 cube is 8. 2 to the 4 is 16. 2 to the 5 is 32. That's the idea. So we can say S sub 2 to the m is greater than 1 plus m over 2 for m greater than or equal to 4. S sub 2 to the m is greater than 1 plus m over 2. Okay? Let me pause for half a second and ask you a question. What the heck are we doing? Why are we doing all this? Right? Let's not lose track of why we are doing all of this. Our idea is to find an expression for S sub n and take the limit of S sub n as n approaches infinity. Are we heading towards it now? Yeah, in a way, right? We now got an expression for S sub 2 to the m to be 1 plus, that is apparently greater than 1 plus m halves. We cannot say equal to what, but at least we know that this quantity is greater than 1 plus m halves. So I'll do one more thing. What if I let n be equal to 2 to the m? Now, can you tell me what m would be? If n is 2 to the m, can I find what m is? I'd be really impressed. N equals 2 to the m. What is m? Log base 2 of n. Right? That's the going from the exponential form to the logarithmic form. You get m to be log base 2 of n. So let's plug that into this expression. Instead of 2 to the m, let's say n. And instead of m, let's say log base 2 of n. Ta-da! S sub n is greater than 1 plus 1/2 log base 2 to the n. Log base 2 of n. Cool. Can we take the limit of this? Can we find what S sub n approaches as n approaches infinity? Well, as n approaches infinity, doesn't log approach infinity as well to the base 2? Yep, that approaches infinity. So this term is the numerator is going to infinity and we are dividing it by a finite number like 2 and adding a 1. So this whole thing on the right hand side is going to infinity as n goes to infinity. So that means S sub n apparently is even greater than that. So definitely S sub n is going to infinity. That shows that as n approaches infinity, S sub n approaches infinity. And so, with a drum roll, we will announce that a harmonic series sigma 1 over n diverges. That is the coolest thing next to sliced bread, right? So a harmonic series diverges is a very interesting concept. And one beautiful, interesting thing. The statement n approaches infinity implies Sn can be interpreted as check this out. As more and more terms of a harmonic series are added, the sum gets bigger and bigger and approaches infinity. Can we say that? N approaches infinity, then that implies S sub n approaches infinity means as we add more and more terms to the harmonic series, that sum is getting bigger and bigger and bigger and is actually approaching infinity. If that is the case, would there be a time when the sum would have crossed 1001, some 10,001 or 10,000, 100,000, right? Obviously the sum is approaching infinity. So in its approach, it is passing a whole bunch of values like 1,000, 2,000, 5,000, all kinds of things. So now, based on that, I'm asking, well, how many terms must be added so that the sum is greater than 1001? I'm not going to ask you any questions on this in a test or I might. No, I might. Sorry. Pay attention to this because it's an interesting one. So, how many terms should we add so that the sum is greater than 1001? And the answer is, well, let's see when it would equal 1001. Sort of. I shouldn't say equal, but yeah, let's see. 1 plus log n to the base 2 over 2 is equal to 1001. Let's do that. And so subtract 1 from both sides and then multiply both sides by 2, and n turns out to be 2 to the 2000, right? So we figured out exactly what n should be, how many terms we should add so that the sum of this harmonic series is just greater than 1001. You like my meme, man? Is that what? Am I now totally woke? I'm using memes to communicate ideas now. A cat is so cute. What? What do I mean by that? How many terms should we add apparently? 2 to the 2000. Okay, let me see. 2 to the 10 is 1024. Okay, so let's just approximate it to 1000. So 2 to the 2000 can be written as 2 to the 10, the quantity raised to 200. So this is nothing but 10 cube, the quantity raised to 200. Okay, approximately. That is 10 to the 600. That's it. Do you know how ridiculously big 10 to the 600 is? if you take all the particles in the universe, particles, I'm not even talking about, hey, the number of sand, the grains of sand on a beach, that is nothing. I'm saying take all your stupid grains of sand from a beach and trees and puppies and everything, the particles, the electrons, quarks, uh, bosons, whatever, muons, all these particles in the what? Not just on Earth in America or something like that. Entire universe doesn't equal 10 to the 100. And here, this we are talking about 10 to the 600 terms. If you add that many terms of this harmonic series, the sum will be just barely greater than 1001. Isn't that mind-boggling? Oh, what? That is slowly diverging, man. So should we say this series, harmonic series, diverges? Yep. You don't even mince words. Harmonic series does diverge. Okay, so that's a good stopping point for this video, and I'll call this as part 1, and I'll have a part 2. Cool. Alrighty.